Hello everyone, welcome to my channel. So today we will be starting a new topic, of course, that would be center of mass, as I have written here. You can see it. So we are going to start center of mass, not from any exam point of view or something. We are just going to learn it. So what actually center of mass is? So let me explain. Center of mass is a point where any body you see, all the mass can be concentrated there, and all the motion of the body can be you know can be take can be took uh, from that point only. For example, I have this pen. Let's suppose it doesn't have any size in y direction or the vertically upward direction. It is just, you know in x direction it has a length, but it doesn't have a breadth. So if I keep it on my hand like this, just stays here. Let me take out the cap. Just stays here. If I bring it like this, it stays here too. But if I bring its center of mass out of it, it falls down. Okay, but it doesn't mean only at the center of mass all the mass of this pen is. There is no mass. The pen is massless from all these sides. If I cut this, that doesn't mean that mass is equally distributed, or it may not be equally distributed, but still it has mass all over its body. So that is the real meaning of center of mass. And yes, so that is the real meaning of center of mass. Before we begin, I want to tell you that I just wanted to explain you what actually it is. So you may not face any problem or something, and I hope you know basics of calculus and integration, of course, because we need to do that for finding center of mass of different bodies. So so we should begin now. Well, I should write the definition, I think, because writing definition would help. Center. Okay, wait. I'm sorry. I should just type it. That would be better. Right. Wait. Okay, let's just write it. And center of mass. Center of mass of a system is a, a point where all the mass can be concentrated can be concentrated. To analyze, please don't mind my writing, I'm just writing with the mouse. Analyze the motion of the body. Okay, so we should, yes, so yeah, of course we should now be able to do this. Now it's obvious, if you mm, if you think like that. If I take this ball, it's a sphere, of course. Ball is a sphere. Okay, wait. I have shapes here. I'll just take the shapes. If I take this ball here, like this, right? So of course, the center of mass will be at the center. If it's okay, that's only if it this sphere is uniformly distributed mass. All the mass should be uniformly distributed all over this sphere. For example, where's my pen? Yeah, here it is. So if this pen Of course, this pen doesn't have like equally distributed mass, so we cannot tell that the distance L by 2 has is the x coordinate of the center of mass. But if its length, half of its length is in the center of mass, but if we assume it to be equally distributed, it's obviously L by 2, like half of the length of this pen. But the cap has different density or different mass. Here the cap has different mass. The rear thing, what do you call that? It has different mass. The refill is different, and there's some empty space here. It's a air too, so it makes a difference in masses. So I hope you understand. And there is one more quality of this center of mass. For example, if this sphere just moves here after a time t, if this sphere just moves here after a time t, then one thing will not happen. Every point, you see, every point on this sphere, this rather this will change its position after time t. For example, like if it moves a distance of 2 pi r, then it's of course going to just roll over and come back to the position. But that is not always the case. Not always it will just move and complete a pure roll, or it may be there may be some lack of friction, so it may, or maybe some friction that it can just stop it from moving like that, or a pure roll. So it can move. It may be like this point A is here. After some time, this point A may be here, but this center of mass will not move from its original position. This is here, and this is still here. No change in position. It is, although it's rotating, but there's no change in its actual position. It's rotating on its axis. You may call it an axis. That it's like passing in this 3D plane. A plane coming out of the screen like that. I hope you got it. So let's begin with our calculations and things. Let's calculate the center of mass of a discrete particle system. Center of mass of discrete. Okay, center of mass is in short COM. Discrete particle system. System. Okay, this video may end anytime, so please don't mind if I couldn't clear or couldn't just complete my sentence. I'll just take the part two, or may complete the sentence in another video, or just maybe some editing and may combine this. But please don't mind. Okay, particle system. So let's take the coordinate axis. Let's. Okay, we are not going in the 3D plane. Okay, it may be in the 3D plane, of course. Why not? It may be in the 3D plane. Let's change the color. What color it should be? It should be red. What? Let's take the 3D plane. Okay, we took the 3D plane here, and we are gonna take 3 points. This, this. Then we are going to take some arrows. Okay, this one's done. Let's take another. This is taking a lot of time. Okay, this is another, and let's take another. Yeah. Yeah, so we have taken three position. Uh, you may call it R1, R2, R3, and this is point A, this is point B, and this is point C. So this is a three particle system. It has three particles. There is no complete such body. So we can find out the center of mass for this. So we can find the position of center mass if we have the position. These are obviously the vectors, position vectors. These. So let's take out like RCOM. RCOM is equal to M1R1 vector sign is M2R2 vector plus M3R3 vector. Okay, this is not like, obviously these are only 3 points. It can be infinitely many points. So we can just take it like that. And it's divided by M1 plus M2 plus M3, so on. So it comes like RCOM is equal to, we can generalize it in a formula. Obviously it is sigma from I equal to 1 to n m I r I whole divided by sigma I equal to 1 to n m I. And yes, of course, because it is a discrete particle system, we have to write it differently. But if it isn't a discrete particle system, the formula is a universal formula. That's not a problem. But if it isn't the a discrete particle system, this m1 plus m2 and m3, all these points will add up to m. This m, this whole mass will be of the whole particle. So that's not an issue. Yes. I hope you got it. This is just the formula. There's no, I don't have any proof for it. You can just memorize it, and it's very helpful for solving questions. If you, I have already explained you with this pen. I hope you understood about it. If you have any doubt, you can just write in the comment section. So, and yeah, so let's take now, if sorry, not discrete, not discrete. Let me see what time it is already. I think only 2 minutes will be lasting. We will be lasting for 2 minutes more. This video will just end in 2 minutes. So I should just not do this. We will just do it in next video, and that will be coming out soon. There's no problem in that. So I hope you got everything I told you like this. This is just for the discrete particle system. Till the discrete particle system, we have done everything. We'll be doing for the whole mass, and we will be then going to find for different bodies like rod, cone, sphere, hollow sphere, and different things. And not hollow sphere or sphere because we know everything about them. We are going to find about hollow hemisphere and hollow or solid hemisphere because that is different from what we think of like sphere. That's the center for the sphere or hollow sphere, whether it is hollow. But the thing is, it should be completely equally distributed mass. Then only it will help. Like I told you, if the center of mass is here, if I roll this like this, center of mass will remain at the same position. Everything may go from one position to another, but the center of mass will remain at the same position as it was always.